From my personal note stash. I took this directly from my personal notes just to present to you guys and explain what I wrote out. And I hope the concepts stick to you because how I arrange this is very helpful in my opinion, but it might not be helpful in your opinion. But I'm just going to go around and explain my notes to you and explain what I think you should know and understand everything and explain some stuff in more detail. So when we're dealing with amino acids, we know there are a total of 20 amino acids we really need to know. Now then, 9 of those amino acids are essential, meaning we have to get them through our diet, and 11 of those amino acids we can produce via bodily biochemical reactions. There are polar amino acids, there are nonpolar amino acids, there are basic amino acids, there are acidic amino acids. The acidic amino acids you need to know are going to be aspartate and glutamate. And we'll look at the structure here in a little bit. The basic amino acids you need to know are going to be lysine, arginine, and histidine. Now, when looking at polar versus nonpolar amino acids, if you recall from my last video, what makes something polar is it has a dipole moment, which makes one of the molecules slightly negatively charged while another molecule is slightly positively charged. And I'll highlight those molecules for you when we reach those molecules. Now, nonpolar means it doesn't have a dipole moment, really. It's just overall completely neutral. And if you recall from the previous video, anything that is nonpolar is hydrophobic. Anything that is polar is hydrophilic. So water-loving for the polar molecules, water-hating for the nonpolar molecules. Now, the polar molecules you're going to find on the outside of your protein, your folded protein structures and your biological structures. So serine, threonine, tyrosine are going to be exposed to the environment. And your nonpolar amino acids, such as glycine, alanine, valine, etc., are going to be on the interior of your folded structures because they don't like water. They don't like other polar materials. So moving on with that. Looking at the nonpolar amino acids, once again, these are going to be your hydrophobic. There's it. Your hydrophobic amino acids, and they're also going to be on the interior of your folded protein structures. They don't like to be exposed to the environment because they're hydrophobic, and majority of your body is made of water. So when this is dealing with biochemistry, majority of the time the hydrophobic nonpolar amino acids are going to say, hey man, just leave me inside. I don't want to be exposed to that water, because once again, nonpolar does not like polar. Polar likes polar. Nonpolar likes nonpolar. So when we're looking at this, we have glycine, leucine, alanine, isoleucine, valine, and methionine. Now, the one I think you really need to look at on here, and I recommend you memorize them all, but if you don't have the energy to memorize them all, do know that glycine is the only amino acid that is achiral. What does achiral mean? If you recall from Organic Chemistry 1, chirality is basically leads to stereochemistry. All the other amino acids, as you can see on here, have what's called stereochemistry. One of the molecules is sticking outwards, one of them is sticking behind. When it's on a dotted line, it's sticking into the plane of paper. When it's on a solid triangle, I don't know how to explain it. The solid triangle line, it is sticking out towards us. It's outside of the plane of paper. So dotted line into the plane of paper, solid line out of the plane of paper, sticking towards us. Glycine, once again, is achiral, so it does not possess this type of stereochemistry. Now, why is that? Now, if we recall from Organic Chemistry 1, when you have 4 different substituents, you can have stereochemistry. When you have 2 of those substituents that are the same, there is no stereochemistry. Well, we have 2 substituents that are the same. We have 2 hydrogens on glycine, making this molecule not possess stereochemistry, making it achiral. It is the only amino acid that does not have stereochemistry. It is achiral. I should also note there are these 3-letter abbreviations for each that you could learn if you really wanted to, but majority of the time, you're not really going to have to know that. Majority of the time, know just the entire name, and you can kind of then reason what the abbreviation is going to be, because, for example, alanine is ALA. If you know alanine, you know ALA is going to be alanine. The abbreviation of alanine would be ALA. There are a couple on here, such as tryptophan and phenylalanine, that do have like weird abbreviations or single letters. Like phenylalanine is F for its single letter, and tryptophan is TRP, which I guess you could get that for an abbreviation, that would make sense, and W, which I don't know where they got W from, but just know that is how to understand this stuff. So moving on, we're now looking at the neutral polar aminos. Once again, these are going to be your hydrophilic because they are polar, they are water-loving amino residues or amino acids, and they are going to be on the exterior of your proteins and biological structures. So if you have a, let's go back to the micelle example, if you recall from my first video. The micelle example would be your hydrophilic heads and your hydrophobic tails. So your hydrophilic heads are going to be these polar amino acids. Your hydrophobic portions, the tails here, would be the nonpolar amino acids that I showed in the previous slide. Now then, what makes these polar is they have, once again, if you recall from the structure of water, it follows the same concept. There's going to be a slightly negatively charged portion of this overall molecule. And as you can see, I have highlighted that molecule that is slightly negatively charged. And this is the molecule on the entire structure that forms these hydrogen bonds. These polar amino acids like to form hydrogen bonds with other polar amino acids. So let's say I have, that's not going to show up very well. H2O present by serine. The oxygen on serine can form a hydrogen bond with the oxygen on H2O. Moving on to the charged polar amino acids that are basic. So these are your basic amino acids that are polar. These are also charged at neutral pH. We should state that again. So with that being said, lysine at neutral pH is positively charged, and it is also basic. Arginine is once again positively charged. It is also basic. Histidine, which on your practice exam is an actual problem, is positively charged at neutral pH. However, there is a special instance with histidine due to this imidazole side group that we will look deeper into further on in the lecture. But for right now, just know these are your basic polar amino acids. So these are still hydrophilic, water-loving. They are positively charged. These are the guys that would most likely form your electrostatic bonds, your ionic bonds with other molecules, so that you could then utilize Coulomb's law to figure out the bond strength with. But moving on, we are now on to our acidic polar amino acids. That's going to include aspartate and glutamate. Now, when they are in their acidic state, meaning they're protonated, it's going to be aspartic acid and glutamic acid. But when they are at neutral pH, of course, they are negatively charged. So aspartate is going to basically be the carboxylic acid that is deprotonated at neutral pH, and glutamate is going to be a carboxylic acid which with an extra CH2 that is also deprotonated at neutral pH. And we will go into a more well, you know what? Let me just explain this concept here real quick also. So let me ask you guys a question. Say we are at pH of, let's say 1. The pH is 1. What's going to happen with aspartate? Once again, COOH, your carboxylic acid, will become protonated, but aspartate, the carboxylic acid that actually forms the amino residue, would also become protonated at an acidic pH. We'll explore this concept further on in the lecture, but just do know that pH has a big effect on certain amino acids, and it's mostly these these acidic polar amino acids and these charged polar basic amino acids. Now, 7 amino acids have side chains that are able to be protonated or deprotonated. This is tyrosine, lysine, arginine, histidine, aspartate, glutamate, cysteine. For the exam, basically focus on these guys. Arginine, histidine, glutamate, aspartate, and lysine. So, we are now on to pH. Now, this is the big portion of what I think you really need to get out of this entire video, is pH and pKa relating to amino acids. Amino acids at neutral pH are what we like to call zwitterionic, meaning they are neutral with an equal amount of positive and negative charges, except unless it's one of those charged amino acid examples such as aspartate, glutamate, lysine, alanine, or histidine. But if it's any of the other ones, it is what we like to call zwitterionic at neutral pH, meaning it is overall, there's no charge on these bad boys. And what that means is the carboxylic acid here is deprotonated, the amide group is protonated, and that makes it overall have that no charge, just making it overall neutral. And that's between pH 5 and 7. You guys probably understand pH, so I'm not going to explain what pH indicates. I think you guys understand that 7 is neutral, higher than 7 is basic, lower than 7 is acidic. So when you're in basic conditions, when the pH is higher than 8, the carboxylic acid here is actually deprotonated, and the amide group is also deprotonated, giving it an overall -1 charge on the molecule itself. So it's not zwitterionic anymore when it's at basic and when it's in the basic conditions. When you are in acidic conditions, I should have wrote acidic conditions in my notes, but here we go now. When you are in acidic conditions, the molecule is actually protonated, giving it an overall +1 charge. And as you can see, the carboxylic acid here is protonated with that hydrogen, and the amide is also protonated, giving it that positive charge. Giving it, once again, it's not zwitterionic anymore, it is now positively charged, 1+ positively charged, because it is not overall neutral anymore. Now then, looking at L-Isomers versus D-Isomers. If a question like this comes up on the exam, just note that proteins in the human body are only in the L-isomer formation. Now, what does the L-isomer formation mean? Basically, the carboxylic acid is on the right side, and the amino residue is also protruding out, sticking out towards us with a stereochemistry right here on the right side. So the L-isomer, is on the right side of the overall polypeptide backbone. The alpha carbon is right here. And yeah, that's the L-isomer. It's basically, these are just enantiomers of one another, if you understand that from organic chemistry too. So basically, these are mirror images of one another. They are what we like to call enantiomers. And the enantiomer that we choose for our that is only found in protein is going to be L-isomer, with the carboxylic acid on the right side and the amino residue protruding out on the right side towards us. And I do have labeled here the alpha carbon. The alpha carbon is this center carbon right here. So now that we understand pH and L-isomers, I want to go back to that concept with how some of these groups can actually change different pHs. Once again, this is going to be histidine at various pHs. At the acidic pH right here, histidine is once again protonated, as you can see here. Well, the backbone is protonated. The amide is also protonated, giving it a positive +1 charge. Excuse me. The nitrogen on histidine is also protonated, giving it a positive +1 charge. So overall, this molecule is +2 charge. Now, when we are at a neutral pH such as 6, the amide is overall positively charged. The carboxylic acid is negatively charged because it's deprotonated. It's zwitterionic. However, the nitrogen on histidine is still positively charged, so we still have an overall +1 charge on the histidine. Now, the thing that's unique about histidine is when it's in this when it's at this neutral pH, it can actually exist in two forms. It can exist in this form, or the hydrogen on the nitrogen here can actually, did not mean to draw it like that, donate its bond inwards, deprotonating, and then giving it a lone pair on the nitrogen, making it overall neutral. And once again, we're back to being a zwitterionic molecule. looking at the histidine at a basic pH such as 10, overall neutral. Imizazole group right here, it's overall neutral. However, the polypeptide backbone is once again going to be -1 charge due to the deprotonation on the carboxylic acid. And the essential amino acids you need to know are histidine, isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, and valine. And do remember, we can only make 11 amino acids. The other ones, which I just labeled, we cannot make. We have to get these through our diet. So these are very important. Make sure you eat your greens and your veggies. That's the same thing. Those are synonymous for one another. I don't know why I said greens and your veggies. Greens are your veggies. So just make sure you eat healthy and you'll get your essential amino acids. But I do think you should know this for the exam. So I hope you guys have a wonderful night. I hope you guys like how this structure is working. Just kind of hitting the concepts I think you need to know. And yeah, have a